Welcome to this video on triangle similarity. Today we'll be proving triangles are similar and using proportions to solve problems. In this first slide, we are looking at two parallelograms and we are trying to determine if these two shapes are similar. And we want to basically set up proportions right next to each other so we can see plainly that all these sides would be in proportion. So if we just kind of match up the sides that would be equal to each other, we can do kind of big side, big shape over little shape. And we do this for all of the sides and see if they're going to end up equaling each other. So if I go down to the top side, I would have 16 over 6. And then I would go to 10 over 4. And then I would go to 16 over 6 again after that. So it doesn't seem like we have similar shapes because we have, if I reduce this fraction of 16 over 6, I would have instead 8 over 3 from big to small. And for the other sides from big to small, I would end up with 5 halves. So these proportions are not equal to each other. So there would not be one single scale factor. I can't multiply 6 by a number to get 16. In this case, it would be about 2 2/3 to go from 6 to 16, but to go from 4 to 10, that would be 2.5. And that is what is shown in our example of these proportions. In this next slide, we are looking through all different kinds of shapes and trying to determine if two polygons are always, sometimes, or never similar. And a labeled diagram would be helpful in order to figure this out. We want to highlight some specific parts of this. The ones that would be always would be equilateral triangles, squares, and regular hexagons. So the idea there is that any regular polygon with the same number of sides will be similar because you have all the angles are definitely congruent. Like squares just have 90-degree angles, equilateral triangles only have 60-degree angles, and all the sides will compare with the same ratio to each other. One interesting example is that if we look at number 2, sometimes two right triangles, that we can kind of look at the same picture with number 7. So sometimes we could show that if they were 45-degree angles in those, then they would work. But if I change this same right triangle to be a 90-degree angle with 60 and 30 degrees, then it wouldn't work anymore. When you're trying to prove these sorts of things, generally you want to start with the always and then try to see never and then sometimes as the third option. And this is very common in proof in that when you're trying to prove something, you're trying to prove that it's either always happening or never happening. And you're looking along the way for exceptions. And it may only be one exception to either of those, but that is where the sometimes part comes in. In this main part of our lesson, we're going to be talking about the different rules that you can use to prove that two triangles are going to be similar to each other. So in the triangle at the very top, we can see that we have a angle A. This angle A right here is the same angle in both the little triangle and the big triangle. So they share that angle, it's congruent. We also have angle B in both triangles, and we have angle C in both triangles as well. So in both of these two triangles, both big and small, we have 3 congruent angles. And if you think about how triangles work in general, if we knew 2 of the angles of a triangle, we can just subtract both of those from 180. So if we only had 2 of them, we would be able to figure out what that third one would be just by using subtraction and addition. So this particular one we can see right here as triangle ABE and triangle ACD are similar. This squiggly line means similar. and that is by angle-angle similarity. Next, we can look at the middle pair of triangles, and we want to first notice that they have an angle in common right here. We have one angle in common, one angle in common right here. Then we want to look at the comparison of the sides. So we don't know what side A and side X are, so we're going to ignore those two particular sides of the triangles. And if we look at the other remaining sides, if we were to compare these together, we have a longer side of 14 and a longer side over here of 21. So if I do 21 over 14 and I set that equal to the 15 over 10, those two proportions are going to be equal to each other. They're both going to be 3/2. And you can see in this next one, we have 3/2 as our scale factor. And this particular one, we're basically saying that these two triangles are similar by side angle side similarity, which we'll define a little more specifically in a little bit. Now, lastly, we have two pairs of triangles where we can kind of go from big triangle to slightly smaller triangle in blue. And we basically have proportions that we can set up of, in this case, little triangle to big triangle, that all three of these fractions are equal to each other. So we can make a proportion out of three fractions sometimes. And we can go ahead and assume now that that is the third kind of similarity, where all three sides of your shape, in this case a triangle, is proportional in size. Now, the three ones I just mentioned, we have first side, side, side similarity. If the three sides of one triangle are proportional to the three corresponding sides of another triangle, then the triangles are similar to each other. And you would write that conclusion, as you can see here, triangle ABC, similar to triangle DEF. The next kind is angle-angle similarity. Remember, we don't need the third angle because it's a triangle. We know it's 180 degrees total. So we know if two angles of one triangle are congruent to two angles of another triangle, then the triangles are similar to each other. And then finally, we have side angle side similarity. So the angle is going to be congruent, and you can see that in the picture in front of us right here and right here. And then we have the red sides are proportional to each other, and the blue sides are also going to be proportional to each other. And you can see in our conclusion that we've highlighted that B and E to be green to show that those are congruent. So in this first example, like we saw earlier on, we can verify that these are proportional sides by making a proportion and set them all equal to each other. So we're going to basically make, from big to small, 3/2 is our first proportion, this side to this side. And then we can basically, it doesn't matter because this is an isosceles triangle, so we can just do 4.5 over 3. And then we have 4.5 over 3 again. All three of these fractions would be equal to each other. They all, if you put it in a calculator, would equal 1.5 if you prefer decimals. Especially when you have decimals already in your fractions, most people would kind of go right to a decimal in that case. Next, we have two examples of angle-angle similarity. In our first one, we know that we have 90-degree angles in both of these two triangles. But we also need to think about our vocab in that this angle and this angle are vertical angles. So that would make them also congruent. And that would mean that we have two similar triangles if we can get two angles that are congruent. In the triangle on the right, we have two right triangles that at first glance don't look to be similar. But if we look a little closer, we have a 90-degree angle in both, so that is a start. But if I know that a triangle adds up to 180, I can do 180 minus 43 minus 90 and get 40 7 degrees. And then if I do the same thing over here, I get 43 degrees. And that would mean that all three of my angles are congruent and definitely similar by angle-angle similarity. In this next example, we want to show that these are similar by side angle side similarity. So we have a good start by seeing that we have a 70-degree angle. And if we look at going from little to big, or big to small, you can see that you double 1 to get 2, double 2.9 to get 5.8. So that's another way, without setting up a proportion, we can see that these are both times 2 for our scale factor. And that means if they have the same scale factor, that's another way of saying that they are in proportion to each other than making and showing 2 over 1 is equal to 5.8 divided by 2.9. So I want you to take a second to pause the video and determine which of these pairs of triangles, which of these groups of triangles would you define as similar, and then we're going to write out the similar type of similarity for each of them. We're now looking at the answers for these three problems now that you've tried them. So if we look at the one in blue, we can see that we can find vertical angles to be congruent, and then we can set up a proportion of 20 over 15 and then 16 over 12, and we can find that we have they equal each other, and they also, you can see that the scale factor is 1.25 for both, making it side angle side similarity. Side angle side similarity. In the top right, we have angle-angle similarity, because if you find a third angle missing in both of these two triangles, you can see that all three of the angles are congruent to each other, and that would mean that it definitely is angle-angle similarity. And then finally, we have two triangles with the side lengths showing. So if I make a proportion and a fraction equal for all the pairs, 18 and 6, 12 and 4, and 9 and 3, we can see that all three of those would be the same thing as 1/3. And you'd be able to multiply the bigger shape by 1/3 to get to the smaller shape. We're going to work through some more complicated examples now involving variables. So first and foremost, we want to look at why we know this is a similar triangle. So we can tell that we have a shared angle right here. So that is a starting point that we know will work. Since we know that we have an angle shared right here, we can also see that we have 90-degree angles in both of these. So in our smaller triangle AEB and our bigger triangle ADC, or ACD, however you want to order your letters, we have two angles that are the same. So now we want to set up a proportion, but first we want to make sure we note that the A to C length of the big triangle, we have to combine the 9 and the 3 together to make 12. And so we can set up a proportion of 9 over 12 for that kind of big, small to big side on the bottom. And then since we are going small to big, it would be 5 compared to that other flat side of x. And now when we're solving a proportion, the best way to do it is by cross multiplying. So I would do x times 9 and 12 times 5 on separate sides of my equal sign. And I would know that 60, in this case, is going to be equal to 9x. And I can just do 60 divided by 9 to get 6.66 for my answer for x. Now let's move to our next example. In this case, we have a similar problem to the one before. So please try to find the answer to the length of RT, which would be this side length highlighted in blue. Now, if I would like to solve this now, I need to show, well, I have two angles that are already congruent, and they have a shared angle up at the top here. So I know I have angle-angle similarity in this problem in general, like so. And then, so now we're just going to set up some proportions here. So I know that I can set up, in this case, I'll do the opposite of what I did before. So I'll do the large triangle, this 12 on the bottom, being compared to the small triangle. And then I know the small triangle has a side length of 10. And we want to figure out the larger length from R to T. So I'll just label it as RT if I wanted to, segment RT. And I'm going to do exactly what I did in our last problem and cross multiply 12 times 10 and 8 times RT. So I have 8 times segment RT is going to be equal to 120. And I just need to divide 120 by 8. And that gives me an answer for the length of RT being equal to 15. In our next problem, we're looking at problems 1 and 2 on screen. So in problem 1, this is something that we will address more in later videos and later lessons. But these two are both isosceles triangles. As you can tell by the side markings that we have here. And so if we think about what isosceles triangles have going for them is that you have two sides that are the same, but also the two base angles are the same, which would mean that this corner angle right here is also 70 degrees. And then if we look over here, we have 40 degrees at the top. So that would mean that we have two angles down here that are equal to each other and would add to 40 to make 180. So it's basically like you're saying we have 2x plus 40 would end up equaling 180. And so if we just solve that for x, we would just subtract 40 and then divide by 2 to get our answer for x. And x ends up being 70 degrees. And that would mean that both of these triangles have two 70-degree angles. And that would right there be enough to say that they are angle similarity. This next problem, number 2, is where things start to become a little bit more challenging for sure. So if I look at what I have here, I have two triangles that are definitely similar. As you can see that they have a angle at the top already that is congruent on both triangles. The other kind of hard to see part about these angles is that you have parallel lines based on these arrows. So these angles that I'm kind of marking with double angle markers, and then the other ones on the other side, those would be corresponding angles, and that makes those congruent as well. So once we know that, we can set up a proportion over here to the right. So I know that I'm going to have basically my large triangle and small triangle being compared. So I can kind of do the bottom sides. So I would have x being over x plus 6. That would have to be equal to then small over large. So I would have 3 over this whole side from A to C would be 3 plus 4.5, which would be 7.5. So here's where things can become a little tricky, because we can do x times 7.5 and get an answer pretty easily. But then we have to do 3 times x plus 6. So I kind of have to write it as a parentheses here for that. So the 7.5x is going to stay the same, but now I just have to distribute that right side so that I have 3x plus 18. And so then you just kind of go through solving the problem by subtracting 3x from both sides to get 4.5x being equal to 18. And then your last step will be doing 18 divided by 4.5. And that means that x is going to be equal to 4. But we need to figure out what BE and CD are. So BE is right here. We got that one. It's 4. But x plus 6 would make CD equal to 10. Problem number 2 is asking us to find both x and y. So we need to make sure we're picking the right sides to make that happen. So we're going to be using 49 as a side, or we got to kind of match up. So the 2 angle markings and the 3 angle markings would match up with 2 and 3. So that means that 49 and 20 are corresponding sides to each other. So they match each other, and that's going to be important because we're going to be using those to find other sides. So up here at the top, we're going to do 49 being divided by 20. So that's our kind of big over small. And then we're going to do big X side. And the one that matches that is the one between the 1 and 3 angle markings. And that would be UW over here. So that would be 29. And so let's kind of just solve this for x by doing 20 times x, cross multiplying again. And then we just do 49 times 29, which would be 1421. And we're going to get a decimal here, but that is okay. So that we have now 1421 divided by 20 equals 71.1 approximately. Now to find y, we're going to kind of start over from the beginning, and we're going to have the same fraction to start with, 49. Let's do it. Let's choose a different color though first. And so we're going to have 49 over 20, again, as our fraction to set it equal to. And then we're going to have y plus 3 that is above its matching side between 1 and 2 would be the 21 up there. So we're going to, just like before in our other problem earlier, we got 49 times 21 and 20 times y plus 3. So we have 20y, and then we have to do 20 times the 3 here to make 60. And that's going to be equal to 49 times 21, which equals 1029. And then we are just subtracting 60 from both sides and then dividing by 20 so that y ends up equaling 1029 minus 60 over 20 is 48.5 approximately for y. And now let's move on to our final problem on this page. We're trying to find x. So we know we're basically going to compare 8 over 14. And we are going to compare the small side of 7 to the whole part over here. So a tricky part here is that this whole side is x and 7 combined, or in other words, it's x plus 7. And now we can cross multiply that proportion by doing 14 times 7 and x plus 7 times 8. So 14 times 7 gives us 98. And 98 would be equal to 8x plus 56. And from there, we can subtract 56 from 98 and then divide that by 8 to get an answer for x of 5.25. This now brings us to our final problem of this video lesson, is kind of an application problem. And so we have we're trying to find the measure of the distance across this lake. which is the distance EF here. And we are located the surveyor at point S. A surveyor kind of looks at the distances across land and elevation changes to create maps and for other many uses in the world. And we want to basically use the same kind of proportions here because we know we can assume similarity in this particular case. So we want to compare and find EF. So we're going to mark that with X. And so we're going to compare 20 from the small triangle to X on the big triangle at the bottom. And then we're going to compare so that we could pick maybe 24 on the small triangle and compare that to 24 plus 30 for this whole length right here. So 24 plus 30 is 54. And all there's left to do is one more example of cross multiplying where we're doing X times 24 and 54 times 20. That means that we've got an equation of 24x being equal to 54 times 20, which equals 1080. And we just need to divide that by 24 to get a final answer of x being equal to 45. And that concludes the presentation on triangle similarity and the proofs that go with them. Thank you for watching.